You perhaps are familiar with something called a salad spinner. This is a kitchen device where after you wash your lettuce, you put it into a contraption where the lettuce sits inside a basket and you can spin the basket. And so what I'm sketching here is a salad spinner in which we haven't put a salad but we put a coin. And when we spin the coin, what we find, interestingly enough, is that the coin will move up and stick to the sidewall. We want to understand what keeps it on the sidewall and what constraints there are, if any, to make that happen. From your experience, you probably realize that um, whether the coin sticks to the sidewall or not, it stays up there, depends upon how fast you spin the basket. If you spin the basket really fast, the coin will go right up and stay right on the sidewall. But as you decrease the omega, the spin rate, at some magic omega, minimum omega, the coin will cease to stick to the sidewall and will slide down. So what we would like to do is we would like to find the smallest omega that will keep m on the sidewall. So towards that end, here is a force diagram, and acting on the coin, there is its downward weight, and there is a normal force acting in this direction, in the inward direction. And if we had only these two forces, there wouldn't be any force capable of holding the coin up, and so we have to therefore deduce that there is a frictional force acting up, and I'm going to label that force as the um, static frictional force. So there's three forces, in other words, mg, n, and f sub s. Furthermore, since the coin is executing UCM, we know it has to be at any instant accelerating inward. And so if you look at this force diagram, you will realize before we even start writing down Newton number twos that the force responsible for giving the coin the inward acceleration is the normal force, as shown in the diagram here. So I'm going to define my coordinate system as shown here, y up, x to the right. I'm going to write a Newton number 2 in the y direction, which says that the static frictional force minus the weight is equal to 0. And then we can rewrite that as, or we can substitute for the frictional force mu sub s times n. And so this would then give me mu sub s times n is equal to m times g. So this then is the static frictional force up, and this mg is the weight downwards. And so they have to be of equal magnitude so they can add to 0, since there's no acceleration in the y direction. Newton number 2 in the x direction says very simply that n is equal to m times a sub x. But because we have uniform circular motion, UCM, a sub x is equal to r omega squared. And so therefore the normal force is equal to m times r omega squared. If I put these two together, and so I'll put, maybe add something in here, then I'll get this equation that you see right here. So mu sub s times n, but n is mr omega squared, is equal to m times g. Okay, so you can see that the masses cancel on both sides, and I can solve for omega squared. Omega squared is g over mu sub s times r, and then omega is the square root of that. So you should be asking yourself, are the units correct? I will let you check those on your own. So let's take an example. Let's take a salad spinner that has a radius of 6.5 centimeters, and let's say that mu sub s was 0.3. Then the omega that I calculate is going to correspond, from this formula, is going to correspond to the minimum omega, because this is the omega at which we're getting the maximum frictional force here, and so if omega was any smaller, this would get smaller, and mg would start winning out over the static frictional force, and the mass would start accelerating downward. So if we plug these example numbers in, we get 22.6 rads per second. I'll let you check that out on your own. And just for practice, let's express that in terms of RPMs, revolutions per minute. So if I take 22.6 rads per second and I change the rads to revs by multiplying by revs over 2 pi rads, and I change the seconds to minutes by multiplying by 60 seconds over minutes, that turns out to be roughly 216 revolutions per minute, or RPMs is the way it's typically expressed. Two questions for you. If mu sub s is 0.2 instead of 0.3, without doing any computation, will omega increase or decrease for m to remain on the sidewall? Okay, second part of this first question is, well, what minimum omega is required with this mu sub s and the same r to keep m on the sidewall? Okay, second question. See if you can devise an experiment that uses a coin and this particular spinner to estimate mu sub s of the coin against the sidewall of the salad spinner.